So today we're going to continue our discussion about reachability, and then we move on to the next topic, which is that of model predictive control. So as you remember from last time, we discussed how a particularly useful application of continuous time closed loop optimal control is represented by reachability theory that essentially involves computing reachable sets through the lens of the Hamilton-Jacobi-Isaacs equation. So we discussed last time what reachable sets are and what they represent. Depending on the interpretation for the target set, we have two main instantiations of the concept of a reachable set, namely avoidance set and reach sets. So what we're going to do today is, based on these definitions, see how we can apply the Hamilton-Jacobi-Isaacs equation to compute these mathematical objects. And then I will discuss how, once you have computed these objects, you could use those in a control pipeline. Any questions? So just as a reminder, we defined an avoidance set, which is a particular instantiation of a backward reachable set, as the set of states at time t satisfying the following definition. A stands for avoidance. This is the set of states for which there exists a disturbance such that for all possible control, the system enters the target set at time t equal 0. And of course, once you have completed this set, you want to make sure that you start outside of this set to guarantee safety. For the opposite, the reachable set is actually the set of desirable states, and is defined as the set of states at time t, such that for all disturbances, there exists a control such that the system enters target set at time t equals 0. So in this case, you would like to start within this set, so that no matter what nature throws at you, you know that there is a control, namely the optimal control, that will still allow you to fulfill your control objectives. So these naturally become constraints in your trajectory optimization problem. You want to ensure that in the case of an avoidance set, your trajectory stays outside of that set. In the case of a reach set, you want to make sure that your initial condition is within that set. Now the question is, how do we compute these sets? So the point is that you can use the Hamilton-Jacobi-Isaacs equation to compute these sets in a very procedural way. Specifically, as we will see, the computation of the backward reachable sets, both in the avoidance case and the reach case, entails solving a differential game where the outcome is Boolean. What does it mean, a differential game? From last time, differential game means that there are two players. We are player one. We use the controls at our disposal in order to either avoid a target set or reach a target set. And then there is player two, nature, that through a disturbance control is trying to thwart our attempt to fulfill our control objectives. Now the question is, at the level of a two-player structure, it should be quite intuitive that actually the Hamilton-Jacobi-Isaacs formalism is well set up to address these problems. The question, though, how do we instantiate all the problem formulation in a way that is aligned with the definition of backward reachable set, particularly because belonging to a set or not is a binary condition. While in the backward reachable set, in the optimal control formulation, we only framed it in terms of a cost function. So the question is, can we reframe membership to a set through the lens of a cost function so that we can reduce everything to the optimal control formulation, to which we can then apply the Hamilton-Jacobi-Isaacs equation? And the short answer is yes. We can encode this Boolean outcome of belonging or not to a target set within the Hamilton-Jacobi-Isaacs formulation by removing the rounding cost, since we only care about being in the target set at the final time or not being in the final set at the target time. There is no notion of rounding cost. And by picking the final cost to denote set membership. The question is how we do that. turns out that this is relatively easy and leads to the level set method for backward reachable computations. Specifically, remember the equations that one needs to solve in order to find the optimal control profile in a differential game. In our problem, we only care about getting into the backward reachable set at the final time. There is no notion of a running cost. So accordingly, we set the running cost G equal to 0 for the specific case of computing backward reachable set. So we are only left with the final cost H, which shows up in the boundary condition for the partial differential equation. Now, can we pick a final cost that reflects the notion that you either belong to a target set or you do not belong to the target set? And the answer is affirmative. So one can always find a function h of x such that set T, the target set, is equal to the zero sublevel set of H. That is x belongs to a given set T if and only if h of x is less than or equal to 0. Let me give you an example, and through the example you see that this is actually quite obvious. So let's assume that the set capital T is represented by a circle with radius r. So T is defined as the set of point x such that x squared plus y squared is less than or equal to r. Now you can define a function h that is a function of, so let's assume that the state space of our system is three-dimensional. So we have a unicycle with state x, the longitudinal position, y, the lateral position, and theta, the heading. So we can define the function h as h of xr, yr, theta r as square root of so if your unicycle, whose state space is three-dimensional, x, y, position, and heading, has x, y coordinates such that h is negative, where is the unicycle? We assume that we have a reference frame like this one. If the function h is less than or equal to 0, where is it?
Inside the circle.
Inside the circle, exactly. Because it means that the distance is less than r. So if h less than or equal to 0, it means x squared plus y squared less than or equal to r, which means that its position, its displacement from the origin has to be less than r, so it's inside the circle. If h is greater than 0, it means that you are outside. And of course, the more h is negative means the deeper you are in the circle. The more h is positive, the farther you are from the circle. So actually, the magnitude of h also has an interpretation in terms of how safe or how unsafe you are. But most importantly, the sub-level set of h tells you whether a system is in the target set or is not in the target set. So then the idea of reframing backward reachable set through the lens of habitable economy Isaacs equation is fairly straightforward. You remove the running cost. This is not a notion of running cost in computing backward reachable sets. You find a function h that represents belonging to a given set, for whatever target set T you have defined. That's always possible. Of course, if you have something that is a bit more complicated than a circle, then the function h is going to be a bit more complicated, but that's not a problem. And thus, we have reframed the problem of avoidance of a target set as the problem of maximizing over u. We want to stay outside of the set. So we want to make us as player one, we want to make h positive. while the enemy, player 2, wants to make H negative. And so we are in the same exact formalism of the Hamilton-Jacobi-Isaacs problem, but the difference is that we only have the final cost. We don't have the running cost. Remember that for the continuous time optimal control formulation, the final time is 0. So we start from some negative time, and the final time is 0. This is more of a convention. So this is an example. So this is an example where the avoidance set is this red circle. For this trajectory here, the cost is positive, since the final point is outside of the avoidance set, which means that the H, the final cost, is positive. And then opposite to that, for this blue trajectory, the final condition is in the circle, which means that H is negative, which means that the overall cost is negative. So we're not doing anything deep here. We're just trying to find a one-to-one correspondence between the abstract problem of backward reachable set computation and the tool that we know of, which is that of Hamilton-Jacobi-Isaacs. Yeah.
Show you like how safe you are? Will it be always be more positive?
Yeah. So that's why actually the magnitude of H not only allows you to reflect the problem of reachable set computation in the Hamilton-Jacobi-Bellman framework, but also give you some interesting additional information, which is loosely speaking a buffer, and information about how much buffer you have before crossing the danger line, which is when H is equal to 0. So short answer is yes. Okay, so we're almost there. So this is the formulation for an avoidance set. So now that you want to, so if you have a problem where you want to find a backward reachable set, that is the set of initial conditions that would lead you to a collision. So for your state to enter some unsafe region for some adversarial selection of this turbulent profile, the problem that you want to solve is a minimax problem. We already discussed how to pick H, and then there is nothing else that you have to do. You just write down the Hamilton-Jacobi-Isaacs equation for this specific problem. Same as last time, we don't have the running cost. And of course, for the boundary condition, we use the H function that represents membership to a given set. If instead you want to solve the opposite problem, that of reaching a goal, so now you want to enter into the set. So you want to make H negative. And the player wants to make, the nature wants to make H positive because it doesn't want you to go into the set. Then the problem formulation is a swap in terms of minimax. And now you want to minimize H. Player 2 wants to maximize the cost. So all stays the same. It's just that the max min and min max are swapped in the conditions. So you would do the same derivation, but just swapping min max. Yeah.
To be used to define a set such that you can enter the feasible set, like iterate.
A set so
get you into that feasible set.
Yeah, I mean, that's a notion of backward reachable set. But by feasible set, what do you mean exactly? Yeah, of course. It will become then your target set, and then you can propagate dynamics even. Yeah, of course. And more in general, we'll see. So I think your question is pointing actually to the next point I want to make here, which is the following. That the formulation so far is pretty static. So basically I'm telling you what is the set of initial conditions such that at the end you are in a desirable condition. But in general, you want to be desirable along your full trajectory, not necessarily just at the end point. Which leads to the notion of an evolution of the concept of reachable set into a reachable tube. Specifically, look at this case. So here we have a case where the trajectory stays outside of the avoidance set. And so the cost is positive. Here you have, in particular because the endpoint is outside. Here you have a blue trajectory, the endpoint is inside, so the cost is negative, okay. But here there is a case whereby the trajectory passes through the avoidance set for some time at t less than 0, but time t equals 0, so at the end, the state is outside of the avoidance set. So the cost, because of how we formulated the problem before, is negative, so we deem this trajectory as safe. Well, I mean, it's safe for the endpoint, but there was a portion of time where you were in the danger zone. Maybe this is a zone where you were too close to another aircraft, so you might have had a near miss. So the question then is, how do we make sure that we protect the full trajectory from being outside of an avoidance set, as opposed to just the endpoint? This leads to the notion of a tube, whereby we want to reason not just with respect to the final time, but across the full time horizon. So basically, you're building a safety tube so that you stay, your trajectory and basically a tube outside it, outside of the avoidance set. Can we still use techniques from Hamilton-Jacobi-Isaacs equation? The answer is yes, we can. I will just give you the intuition here, because this gets a bit more convoluted. But essentially, the intuition is as follows. So before, so in the setting of reachable set, you cared only about the final endpoint. Now you care about making sure that your entire trajectory stays out of the avoidance set. How do you change the problem formulation such that you encode this objective? So one way that you could do that is by replacing h of x0 as your cost with the minimum of tau in the optimization horizon of h of x tau. So what this is saying is that you are interested in making sure that not just h evaluated at x of 0 is greater than 0, which means that you're safe, but that the minimum of h across all of that trajectory is greater than 0. Because if that is the case, it means that at every single point in time, h evaluated at x of t is greater than 0, which means that you are outside of the avoidance set. Make sense? So basically, you are strengthening, or actually making your cost a bit more sophisticated to encode the notion that you don't just care about what happens at the end of the optimization horizon, but you care about what happens throughout the horizon. In particular, you want to make sure that you're in the worst possible situation across your optimization horizon, h never dips below 0. Now, this is a cost that we haven't seen last time. So actually it changes a little bit the derivation that we did. We're not going to do the derivation, but basically the Hamilton-Jacobi-Isaacs equation takes this form that is a bit more complicated because now we have an additional minimization, and I'm not going to dig much deeper than that. My main point is that if you care about making sure that your entire trajectory stays out of danger, there is actually a formulation of optimal control that allows you to compute that object. It's a little bit of a refinement of a Hamilton-Jacobi-Isaacs equation. We're not going to go down this path because we have many other concepts to discuss in this class. But if you're interested, I provided you with the references to do so. My most important point here is to make sure that you are familiar with this problem and you know that there are tools at your disposal to solve it. Yeah?
So both the BRS and the BR2 refer to like a set of initial states.
Yeah.
So what is the...
But with a different property. So here you make sure that it's a set of initial states such that you don't end up in danger at the end of optimization horizon. This is the set of initial states such that throughout the optimization horizon, you stay out of danger.
Are we solving for either the BRS or BR2, or are we solving
for two things? You're solving for the BRS, and you're solving for the optimal control profile U. So I mean, you start from the from a state in the backward reachable set, okay? But if you don't use the optimal control policy, you might still, so actually in the case of the avoidance set, you start with initial condition outside of the backward reachable set. But if you don't use the optimal control policy, actually the disturbance might still lead you into the avoidance set. So you need both the set and the associated optimal control policy. But the optimal control policy, once you have solved for the Hamilton-Jacobi-Isaacs equation, can be computed quite readily. So this is an easy computation. So once you compute the backward reachable set, you can also easily compute the optimal control. Yeah.
So like what you were talking about with reaching versus avoiding, when you switch maximum to min-max, in the value function in the backwards reachable tube, does the outside...
So here there are two things, right? So there is avoid versus reach and tube versus set. So this slide is only about avoid versus reach. There is no notion of tube here. Yeah.
Is there any notion of reaching for tubes? Like if you want your agent to pass through a certain corridor?
Yeah, there is, even though it's slightly less commonly used. So typically, even though I frame the problem also from the point of view of reach, typically reachability-based computations are used more for the purposes of safety. To basically, the additional constraints you have in your trajectory optimization process to make sure that you have enough buffer to avoid collisions or stuff like that. So the most common formulation is the avoidance safety one. So let me show you one example. And of course, the set of initial conditions for which you're guaranteed to stay out of danger is that such that the value function is greater than 0. Now, let me show you an example to make these things a bit more concrete. Yes?
If our dynamics make it such that we can never reach our target set, what happens when you're trying to initialize our initially target set?
Yeah, basically your set is empty. And either you change the problem or you don't control, basically you don't deploy your robot. But at least it gives you strong information. It means that the way you frame the problem, maybe because you were too conservative, it might be that your problem formulation is too conservative. Maybe you don't have enough control actuation, so you want to spend a bit more money on buying better actuators. But it's saying something about your problem formulation. Maybe it's just how you frame the problem, or maybe there is an inherent limitation in your robot. And then, for example, you have to design a better robot, have more control authority. But yeah. So let me show one example. So this is actually quite illustrative. So we have a situation whereby we have two airplanes modeled as with unit cycle dynamics. So the equations of motion for the first airplanes are x dot equal v cosine of theta, y dot is equal v sin of theta, theta dot is equal u. So essentially the state space is three-dimensional, x, y position, and heading. And you control the heading theta. So basically the time rate of change of the heading through the control u. And the vehicle goes at speed v. Same equations of motion for the other vehicle, x dot equal v cosine of theta, y dot equal v sin of theta, t dot equal ub. So now I pose you this question. So what is the initial set of, what is the set of initial conditions joint, so between aircraft A and aircraft B, such that there is a trajectory for aircraft B that no matter how much we're trying to avoid a collision, might lead to a collision. Whereby by collision, we mean that the relative position between A and B is so the relative distance is less than r. So essentially, our avoidance set is indeed a circle in the relative position xa minus xb and ya minus yb. We want the relative distance between the two aircraft to be less than r. So if we center everything around aircraft A, we want to make sure that B is never inside this kind of ownership circle. So what is the set of initial conditions that allow us to make sure that a collision, or at least a near miss, never happens? So we are exactly in the setting of a computing an avoidance set and associated control profile for player A, that is us, to avoid a collision. So I posted a script. Is the problem clear? Any question about the problem set? I mean, this is the real stuff. I mean, how people may want to implement some level of collision avoidance for aircraft. So I implemented a Jacobi reachability computation. So this is useful because it gives you a reference code base to do this type of computation. But here, in particular, I want to show the main result. So I implemented the dynamics of these systems. So this is not too important. I will just highlight here, even though it's a bit small, that basically the terminal set, the terminal values is defined as the circles with radius 5. So that's where I implement the H function. So I call a package, we code it up in my lab called HA reachability. This is essentially the end result of an HA computation. So what is thing saying? It's a weird shape. So X represents in relative coordinate the relative longitudinal displacement. So if this is aircraft, so this distance here will be X. This distance here will be Y. So what we have here, and Z is the relative heading between the two aircraft. Okay? So this is the zero-level set of the cost function as computed through Hamilton-Jacobi-Isaacs equation. Which means that if for those set of states for which J is negative, namely you are within this green shape, then you might end up in a collision. If you're outside, you don't end up in a condition. Why this weird shape? So to illustrate how to interpret this result, so this is basically the set of states for which J is equal to 0. Assume that Z, the relative heading, is the relative heading is 0. So basically the aircraft are aligned. Well, so if this is the case, then in order to be out of danger, since just the aircraft can follow each other, either they start outside of the circle and they will stay outside the circle forever, or if they are inside the circle, we just say inside the circle forever and they are in a danger situation. So that's why the backward reachable set has simply the shape of your avoidance set. But let's see what happens when Z, the relative heading, is close to 3, which basically means pi. So it takes a little bit actually of practice to view all of this, but then it becomes quite intriguing. I don't know why it's not picking this up. So this is the part where I had to show my computer. It's very difficult to show the shape on the board. Yeah, so let me try to make it a bit bigger. So say that, told you that it's a little bit tricky. So, come on. So say that you are pi equal 3, so that the aircraft are opposite of each other. And so this axis is still the longitudinal displacement. So what is it saying? That if you are with a positive longitudinal displacement, namely the aircraft, so this aircraft A, so aircraft B is here, in order to ensure collision avoidance, initially the aircraft have to be more separated. because the other aircraft is just pointing at you. So you need a little bit more maneuvering space in order to avoid the other aircraft. If instead the aircraft is beneath you, then no problem. The only thing that you care about is that you don't start in a situation where you are already within the circle, but then otherwise you can just escape. So that's why you have this kind of protrusion in this direction to take into account about the geometric part and dynamic part of the problem. Does it make sense? So this is just saying something obvious, right? That if the two aircraft are on a collision course, you need to have a more lateral separation. That's what this blob here is saying. But it's kind of nice that we computed actually from first principles, and we know exactly for then each possible value of the relative heading by how much you want to ensure lateral separation, also taking into account longitudinal separation, also taking into account about lateral separation. So now I can tell you exactly how much longitudinal separation you should have if you start from this initial condition, or if you start from initial condition, or if you start from initial condition. Of course, this one, from the point of view of avoiding collision, is worse than this one. And this is actually reflecting this kind of non-symmetrical shape of this object. Yeah.
Constant velocity.
Yes, V. Yeah. Otherwise, that you can also choose two different velocities. Of course, the shape of the thing will change. Just to reiterate on the concept. So here I'm showing how the projection of the backward reachable set changes depending on how long the time horizon is. For now, let's just look at the black curve here. Blue means negative. I mean, darker blue means negative. Everything else means positive. So here is the scale. So this is essentially the projection of that weird thing that was three-dimensional on a 2D space where we fix the relative heading at 3.7. So a bit higher than pi. X, still notion of longitudinal distance. Y, notion of lateral distance. So we're fixing the relative heading at a little bit more than pi. So it's basically something like that. So the vehicle is pointing, the vehicle B is pointing in this direction. And then you want to understand where it should be placed at the beginning to make sure that we do not incur a collision. So fix the longitudinal separation equal to 5. So if, and then my point is why basically the reachable set has this shape that is a bit tilted. Well, if you fix the longitudinal separation at 5, then do you want to add more lateral buffer if the vehicle, so we're fixing the longitudinal separation, right? So the question is, do you want to add more lateral safety buffer if the vehicle starts with a negative lateral distance or with a positive lateral distance? In other words, do you think that this situation is safer or this situation is safer? Who votes for option 1? Who votes for option 2? Great. Happy to fly with all of you. So yeah, of course, because this guy, in order to really collide with us, we need to do a much more complicated maneuver, and we have much more space to evade. So that's why now the reachable set is tilted. It's simply saying that if you are you start with a negative lateral distance, you need less buffer. With a positive distance, you need more buffer. You need up to 5, say, meters. What is saying, why is this thing evolving through time? The shape of the reachable set, of course, depends on the initial time. So if you are computing the backward reachable set from the perspective of time equal to minus 2.5, minus 3, minus 3.5, remember that the final time is always 0 for these computations. So it turns out that after 3.5 units of time, actually the backward reachable set goes to a constant. So after minus 4, minus 5, minus 6, you always get the same backward reachable set. Why is that the case? Is that in most of these problems where things are stationary, after a transient, then the problem set up into a stationary situation whereby either the player 2 is just chasing us, or we have collided. So it doesn't change that we have more time at our disposal. And let me show you some example of, so you do this computation, you compute the control profiles, and then you start injecting some possible initial conditions. And here I picked 3 for fun. So blue is player 1, red is player 2. So we want to make sure that player 2 doesn't enter our personal space. So here is a situation where we started, in terms of relative coordinate, outside of the backward reachable set. So no matter how hard player 2 is trying to play the game to catch with us, it can't. Velocity here is the same. You see that after a while, then you just go into a steady state. Additional time doesn't really buy you anything. So this is a situation where we started with player 2 essentially inside the personal space, and then it just locks in, and then it stays in our personal space throughout. Here is an interesting case that I found, whereby the player 2, for a little while, transition in our backward reachable set, in our protected space. But then we're able to maneuver out, and then the other player is unable to catch with us. So for the way we frame this problem, we have succeeded. In reality, we should care about the fact that for some small portion of time, actually player 2 enter our personal space, so this is undesirable. So this is motivation for actually switching to backward reachable tube formulation, which is not what we're doing here. So that's why for this computation, actually this is a success story, but in reality, probably we would like to use a backward reachable tube formulation, in which case this would be a negative story. So but what I'm doing here is just to initialize the two vehicles inside or outside the backward reachable set, playing the game optimally as derived through the solution, the Hamilton-Jacobi-Isaacs equation, and then displaying the trajectories. Isn't this cool? I think it's nice. And people use this stuff for real. So for example, in several production grade autopilots for cars, you have something reminiscent of a backward reachable set to ensure that at the lowest level of safety, no matter what another driver might do close to you, you still have a safety buffer so that you can maneuver around. Yeah?
Is the BRT guaranteed to converge for some?
The backward reachable tube. So first of all, here we're not computing backward reachable tube. We are computing backward reachable sets. In general, for a time varying formulation, it converges to a steady state solution. I think it's pretty neat. I know that mathematically, probably this was the most sophisticated lecture. I tried to give you as much intuition as I could. The treatment of differential games, mathematically speaking, is quite involved. But I do hope that at least you have an understanding of the main ideas about what is possible with this formalism, and also what are the underlying algorithmic packages that allow you to, algorithmic concepts and packages that allow you to solve these problems. And speaking about algorithmic packages, how do you solve this stuff? Well, solving a partial differential equation is hard. Actually, the example that I gave you is based on a package we developed in my lab, which is one of the fastest packages written in Python to solve Hamilton-Jacobi distributed equations. So you could use that. That said, typically, you can solve these problems for maybe 5-dimensional state space, 6-dimensional state space, and then things break down because of the Carso dimensionality. So the solvers don't scale beyond that dimensionality. That said, doesn't mean that you can't solve a reachability problem with more than 5-6 dimensions. You just have to resort to approximations. And this is still a fairly active field of research. There are many different ways of breaking the scalability barrier by using approximations through neural networks, sampling-based methods, giving up some guarantees of accuracy, and so on and so forth. So I won't go into the details here, but at least you have an exact implementation of Hamilton-Jacobi reachability computations through the AJ package that I showed you before. And then just for you to know, there are a number of techniques that are approximate in nature that allow you to solve this problem beyond 5 or 6 dimensions. All right, let's move to MPC. Any questions in the meantime? Comparatively speaking, MPC is going to be a walk in the park in terms of complexity. MPC is actually very intuitive in general. It just feels right, I think, as a control strategy, as you'll see. Going back to roadmap, so we spent quite a bit of time on open loop optimal control. We spent quite a bit of time on closed loop optimal control. This is fast, but less powerful because you reason in terms of open loop control sequences. This is powerful, you reason in terms of closed loop policies, but computationally complex, both in the discrete time formulations through the discrete time Bellman equation or in the continuous time formulations through Hamilton-Jacobi-Bellman and the Hamilton-Jacobi-Isaacs. Can we get the best of both worlds? Basically, the speed of an open loop control method with the power of a closed loop control methodology. The answer is yes, to a large extent, through the lens of MPC, model predictive control. MPC is really a framework more than a specific control strategy. That said, I would say that after PID controllers is probably the most widely used control methodology out there. Originally developed in the 70s and 80s more as a heuristic, primarily in the chemical engineering domain. You may wonder why chemical engineering? Because of 2 reasons. First, there was a need. You want to reason about constraints. Typically in chemical engineering, you don't want the temperature of the products that you're mixing to go out of whack. So you really care about constraints, otherwise the entire thing blows up. And constraints are difficult to be dealt with directly through frequency-based controls. But at the same time, chemical processes typically evolve on a slower time scale, multiple seconds. So even though MPC relies on, oftentimes, online optimization, and at the time the computers were not particularly fast, people could still solve those optimization problems at a level of a few seconds. So it was just a sweet spot. There was a need, and actually the problem itself was well attuned to solve optimization problems at maybe 0.5 hertz or 0.1 hertz. So what we're going to do today is to introduce the basic ideas behind MPC and start developing a bit of theory about how to apply MPC in a principled way. Good readings about MPC are the textbooks from Borelli, Benporad, and Morari, and the textbook from Rawlings and Main and Thiel. These scientists, in general, have been quite influential in setting up the algorithmic foundations of MPC. Until the early 90s, MPC was used mostly in heuristic, and then people in the 90s and 2000s started developing a theory about MPC that allow researchers and developers to deploy MPC with mathematical assurances about the correctness of the design. Most recently, as you know, there have been a lot of advances in terms of online solvers. So that has been the main trend, to really push MPC into the control loop with increasingly more stringent requirements in terms of replanning rates. 10 hertz, 30 hertz, kilohertz, and so on and so forth. So what is MPC? The idea of MPC is really, really simple. And as I said, very natural. So the underlying idea is that you have an infinite horizon optimal control problem, and you want to solve it optimally, but that is very expensive. And so you're fine with solving it suboptimally, but still in closed loop form. So what does MPC do? MPC measures and keeps basically track of previous values of the states. Based on that information, based on information about the dynamics, based on the control and state constraints, it computes a control profile. Here we're assuming that we are solving the problem in discrete time. So essentially it solves, an open loop optimal control problem over a finite horizon between time t at time t plus np. You find that your open loop control sequence along with a predicted sequence of states or outputs that stem from the application of your optimized control sequence to the dynamics of your system. So far, this is just open loop optimal control. But then what the MPC does is to use only the first control that makes the system transition to the new state or output at time t plus 1. And then you completely discard everything else that you computed at the previous planning cycle. And you recompute everything from scratch, but now starting at a new state at time t plus 1. With the idea that at every single planning cycle, you always solve for an open loop control problem. But since you replan, which means that you get to observe a new state, and based on that, you solve a new open loop optimal control problem, you actually endow the entire framework with a notion of closed loop, because you are closing a loop on your most recent observation of the state. But you're always solving an open loop control problem. Turns out that this is really a sweet spot between doing open loop optimal control and actually using closed loop information from the measurement of the state. It seems wasteful, right? Because you solve the problem over maybe a long horizon, and then everything that you have computed after the first time step goes into the trash. Not always, because you can always use this information to inform the solution at the next step. But in its simplest vanilla form, you put everything into the trash. There are some nuances, like for example, you may want to compute your optimal control sequences up until an horizon t plus nm, but keep your predictions going for a little bit farther. So there are a lot of variations in the team. So MPC is a framework. It's not a specific control algorithm. But the main idea is that you do receding horizon optimization, always moving, which again is very natural. It's also what we do as humans. We optimize our control profile, then we walk around a little bit. Of course, we gather information and we revise our plan. So the idea shouldn't be too surprising. Does it make sense? There is a little bit of notation here, t plus 1 plus k given t1, t plus 1. I will explain this terminology in a second. So key ideas. At each sampling time t, we solve an open loop optimal control problem over a finite horizon. How long that horizon should be, we will discuss it later. We apply the optimal input signal during the sampling interval t plus 1. We throw into the trash everything else. Then the system, under the application of this input, evolves into the new state at time t plus 1. And now at time step t plus 1, we solve a new optimal control problem based on new measurements of the state of a shifted horizon. So now the horizon goes one step into the future. So let me give you a little bit more concrete formulation, particularly in the setting of linear dynamics. So we consider the problem, again, of regulating to the origin, the discrete time linear time invariant system, xt plus 1 equal ax plus bu. So very similar to what you would do with the classical frequency domain control. But we also have constraints, so this is not something that you can do with classical frequency-based control. So we assume that the state x belongs to some capital set x, so the set of safe states, and u belongs to some capital set u. And here we're assuming that the sets X and U are polyhedra. That is, there are sets that can be defined by finitely many linear inequalities. So basically half planes that defines your feasible state space. A cube, for example, we are confined within a cube. So what is the basic formulation of MPC then? Assume that we can measure fully the state X of t. Then at each replanning time at t, we solve an optimal control problem in open loop in terms of the variables ut, ut plus 1, all the way to ut plus n minus 1, to minimize an additive cost, but now you should be very familiar with the structure. So you have a terminal cost plus the summation of a running cost, subject to the dynamics, state constraints, control constraints. The initial condition has to be xt, the state you are in right now. That's how you close the loop. And also potentially adding some terminal constraints. So you want to make sure that your predicted state after n steps belong to some desirable set x of f. I will discuss later why we may want to add this constraint. So you solve for this optimal controlled sequence. You use the first term. You move into state xt plus 1. You measure it, and then you replan. Where is all this complicated formulation here coming from? You know, yes, so this vertical bar, t, and so on. What does that mean? So that means the following. So xt plus k given t, just terminology, is the state vector at time t plus k predicted at time t via the system dynamics. Ut plus k given t is the input u at time t plus k computed at time t. Note that the state predicted at step 3 from the perspective of time 1 is not necessarily the same state 3 predicted from the perspective of time 2, simply because maybe these turbulence might have perturbed our nominal trajectory. Any questions here? So here what I want to highlight is these two guys. So these two guys are additional terms that we inject in our MPC formulation to regularize it. You know, our optimal control formulation basically has the running cost, has the control constraints. Where are the terminal constraints coming from? And where is this auxiliary cost that is placed on the predicted variable at time n coming from? So those two terms are actually the two designing choices or tuning knobs that as MPC designers you can tune in order to optimize the performance of an MPC control framework. So what we will see for the rest of this lecture and then the lecture on Wednesday will be to see how do we tune this auxiliary terminal constraint here, these terminal cost here, and potentially the n, so how much look-ahead steps you have, to make sure that you have a good formulation, good performance once you deploy MPC. And in general, you care about two things. First of all, you care about the so-called notion of a persistent feasibility. So you want to make sure that once you transition into the new state, the new optimal control problem that you're trying to solve is still feasible. Otherwise, you're stuck. I mean, that's back to your colleague's question before. What happens when the reachable set, for example, is empty? You don't want to end up in that situation because it means that you're stuck. You have nothing that you can do. Whatever you do, basically, you're going to violate a constraint. So how to make sure that that doesn't happen? So how do you play with your tuning knobs so that that doesn't happen? And then, of course, assuming that that doesn't happen, how do you make sure that you fulfill your task? In this case, regulating the state to the origin. So you basically want x go to 0. Okay, so we talked about the terminology. Before we address the two questions I mentioned before, let me add a little bit more notation, but not too much. So as I said, what you do in MPC is you take the first control in the optimal control sequence that you have computed, which is a function of the state, because the first predicted state has to be equal to the current state, x of t, of course. And that's the control that you enact on your system. Then the optimization problem is repeated at time t plus 1, but with a new state constraint that the state predicted at time t plus 1 from the perspective of t plus 1 has to be the state at time t plus 1 as measured. So now we can define a closed loop policy as the first control input that is determined when we solve the optimal control problem starting from the state x of t. You see how actually this is how we are closing the loop and bridging the gap between closed loop control sorry, and the open loop optimal control. Is this point clear? That's a little bit the crux of MPC. So then the closed loop evolves as xt plus 1 equal ax plus b pi, which we can abstractly written as a closed loop function of x and the time. So how do we characterize the closed loop behavior of this system? One more thing notationally, and I know this is a bit boring, but it will be needed later, is that in the case that the problem is time invariant, that is, A does not explicitly depend on the current time, so there is no subscript k. B does not depend on the current time. C does not depend on the current time. So this problem, the only thing that changes across planning horizon is the initial condition for the state. So we can write it in a simple form where we drop all the thing of predicting from perspective of time t and so on and so forth. We can just drop all that terminology and use this simpler formulation. But with understanding that we solve this problem, starting at state x of t, we use the first control u0, we transition into a new state xt plus 1, and then we solve the same problem, but now with x0 equal xt plus 1. Yeah? Oh, you also have some comment.
Oh, sorry. So does this formulation require that our time horizon is long enough for the final state at time n or time?
Yeah, otherwise you may not get there. Yes, yeah. I mean, in general, the best way to see MPC is that the underlying problem you're trying to solve is on an infinite horizon, which, as we discussed before, is a bit of an abstraction, of course, but a good framing.
Does that then make it so if your time horizon is shorter, you might have more aggressive control?
Yeah, you're more greedy.
Okay.
So, and actually, if it's too short, you may not actually converge and regulate your state. So that's why the time horizon, the terminal cost, P, and the terminal constraint, X of F, are crucial to tune to make sure that you properly balance look ahead capability, so how long in the future you optimize over, which is in general, the longer the better. You make your decision more informed, but you pay more computation cost. And how short your term horizon is, in which case you might be too greedy or even myopic, in which case you may not fulfill your task. So it's going to be a delicate balance between how much computation time you want to invest versus whether you can actually achieve your task. Okay, so in a simplified notation, then your optimal control is the first control input that you compute in the previous optimal control formulation, and then you have a closed loop control law. Now, with what type of cost functions do people use? Here, there are not many surprises. So for the running costs, quite common to use just a quadratic cost similar to LQR. Or you might use also some other P norms, where, for example, you could use the 1 norm or the infinity norm. The 1 norm of a vector I'll have a marker. Okay. Is the sum of the absolute value of its component instead of the square. So to wrap it up, in online model predictive control, we measure the state x of t. We solve finite time optimal control problem. If, God forbid, the problem is infeasible, you're stuck, you call for help. Otherwise, you apply the first element u0 to the system, you transition to the new time t plus 1, you measure xt plus 1, and you repeat. Why online? Because here the idea is that we are solving this problem online, so as you are deploying your system. As we will discuss briefly next time, there are also offline formulation, whereby you do the optimization offline, basically anticipating all possible conditions that might arise. But for most of this exposition of MPC, we will consider only the online version. Right, so what I was mentioning before is what are the things we care about? So the two things we care about are persistent feasibility and stability. Persistent feasibility, we want to make sure that the optimal control problem is always feasible. That's quite obvious. Stability means that we want to make sure that the genetic control inputs lead to trajectories that converge to the origin. So the question is, how do we tune the three main design knobs so that these two objectives are fulfilled? Up until the 90s, this was mostly heuristic. Then between the 90s and 2000, that's where people started putting some theory to allow you to make informed choices about how to select those tuning knobs. So, sorry for the cough. That's what we're going to discuss next. So there are two possible ways of approaching the problem. The first one is a closed loop system, right? So we have xt plus 1 equal f of a closed loop of x of t. We try to somewhat analyze how the dynamics of this closed loop system evolve depending on the three tuning knobs, and then we optimize the three tuning knobs. That's very hard because this is a nonlinear system that entail an inner optimization. So this closed loop function f is really the result of applying an optimization step, so it's difficult to analyze. And that's where the people were stuck. Then people realized that a better way to do that is to directly derive conditions in the terminal function p, the terminal constraint set xf, so that the persistent feasibility and closed loop stability are guaranteed by design, without having to analyze ad hoc the trajectory evolutions. So what we're going to do next is to first tackle the problem of persistent feasibility. That's the most basic one. If you can even solve the optimal control problem, then the question of stability is not even relevant. And then we're going to see how we can, once we solve the problem of persistent feasibility, address the problem of stability. So let's focus on persistent feasibility first. So the goal is to tune our tuning knob so that feasibility for all future times is guaranteed. To address the problem, we leverage tools from invariant set theory. So I'm going to give you a little bit more terminology, sorry about that. MPC is a little bit less mathematically intense than reachability, but it's a bit more boring in terms of terminology. What is an invariant set? So let me first pin down a little bit of terminology. So we define the set of a feasible initial state, capital X0, as the set of states that are feasible, meaning belong to the set capital X, such that there is a feasible control sequence. By feasible, I mean that each control UK belongs to capital U, such that the evolution of the state trajectories stemming from the application of this control sequence gives rise to states that are feasible at all times, and such that the terminal state belongs to the desired final set. So this is a set of initial conditions for which the optimal control problem has at least one solution. A control input can be found only if our current state belongs to this set. Then we define the notion of a controllable set. For an autonomous system, xt plus 1 equal to phi of x of t with the state and control constraints, the one-step controllable set to set S is defined as the set of states such that after one-step application of our transition dynamics, we end up into set S. Yes, great, thank you. Specifically, say that you're given a set S. The question that you are asking is, what is the set of states referred to as PRE, or previews of S, such that if you start here, and then you apply your dynamics, f of x, you end up here. So you're given a set, you're trying to answer the question, what is the set of state, such that after one step, under the natural dynamics of the system, I land into S. The notion of a one-step controllable set extends to the case of a controlled system, where now xt plus 1 is a function of x and u, where the definition is very similar. The only difference is that now we define the one-step controllable set as the set of states for which there exists a u, such that a one-step application of our dynamics leads us into S. So there exists a u such that f of xu leads me into S in one step. Okay, that's just a definition. One more set of definitions. So another important definition is the notion of a control invariant set. Actually, this is a concept that arises quite ubiquitously in model predictive control. A given set C is a control invariant set let's call it DC. A given set C is a control invariant set for a given system xt plus 1 equal f of xu if you start in C, so this is your state x of t, then there exists a control u such that under the state transition dynamics, you land in C. So if you start in C, think of C, say, as the safe set, the set of relative states where you are far enough from danger. There exists a u that allows you to stay in that set, which seems a useful concept. So there exists a u such that f of xu lands into, again, C, the same set. So of course, you want to choose a C as a set of desirable states. The set C infinity, this is really just a minor notation, is said to be the maximal control invariant set if this control invariant contains all control invariant sets containing X. It's basically the largest possible control invariant set that you might have for a dynamical system. Similar definition arises for autonomous systems, so systems where you don't have explicit dependence on the control. A set is said to be positive invariant if after one application of the, so if you start in the set A and you apply your dynamics, you still remain in A. So these sets can be computed by using a fairly powerful MATLAB tool called MPT. And actually, you will use this tool as part of your homework. Yeah?
How a control invariant set could not be maximal? Like an example of a set that...
Yeah, I mean, sure. I mean, you might have a control invariant set with this definition, but no one is telling us that there might not be like an extension that still has this property. So actually, you must, so for example, a control invariant set could be 0 for, I mean, literally the set with a single point 0, whereby if you have a linear system and you start a state equals 0, and use control u equals 0, the next state is 0. So the origin typically, you see what I'm saying? So you start at the origin, x equals 0, assuming that the control u is a feasible control, then ax plus bu is still 0, which means the next state is 0. So that's a control invariant set. But that doesn't mean that there might be some other states that actually still allow you to transition into the same set. We'll see actually some examples later. All right, so let's get to the first useful result related to feasibility, which is as follows. So let's define X1 as the truncated feasibility set. So the set of states for which the problem now solved over an horizon n-1 is feasible. So this is the set of states such that there exists a truncated control sequence starting from U1 and not U0, such that it is feasible, that UK belongs to U, and so that under the application of the dynamics, the states satisfy the state constraints and satisfy the terminal constraint. Key result is as follows. If set X1 is a control invariant set for your system, then the MPC law is persistently feasible. The intuition is that basically if X1 is control invariant, you can use this control invariant to buy one step of staying in that set and then solve the problem for n-1 steps. Now, the result per se, I mean, we'll prove this result next time. The result per se is completely useless because your tuning knobs are XF, are the terminal cost P, and are the horizon N. You don't really control this, you don't really tune X1. But as we will see, this is a useful lemma that allows us to then derive a theorem that is actually actionable, allows us to tune the tuning knobs that we have in MPC. So we'll prove this lemma next time. It'll take 5-10 minutes at most. And then we'll continue our exposition about persistent feasibility, and then we move into stability. The end result will be a set of conditions that tells you explicitly how to tune a Pn and a terminal set X of F to ensure persistent feasibility and stability. And then in your P set, you will solve a few problems so that you really appreciate this theory. All right?